heard versions of this talk before, but that will include a certain fraction of the audience since, well, some of you have worked on the subject, and I've been talking about this off and on for the past 4 years, I suppose. But this should be new to some of you, and I will hope to have a few new results at the end that will interest even those who've heard this kind of thing before. So before starting, let me say I tend to be very bad about giving citations and references. So in order to avert that catastrophe of not citing anyone, I've put some of the relevant names on the board. These are some of the relevant names from the last few years. There are other relevant names from the preceding few years that I'll try to work in at the right places, Simon, in the talk. And in particular, this sort of whole program was something that was developed largely in collaboration with Veronica Hubany and Mukund Rangamani. So it's especially important to bear in mind their names if I'm not citing papers and collaborators. But the following people have also contributed to this general line of work. Figueres, so Pau Figueres, who's here at Cambridge. My student Sebastian Fischetti, who I'd like to introduce you folks to. He's slowly waving his hand back there. He can answer most technical questions. Veronica Mukund. Pau's student. Pau, help me with the name. Or perhaps he's here.
You can use his first name, Saran.
Is he here?
He's not.
Too bad. I was going to have him wave too. All right. Students get introductions. George Santos, who was a postdoc in Santa Barbara, now at Stanford, but is joining the faculty here. Toby Wiseman, whom you all know, and Benson Wei, recent arrival and now a postdoc here at Cambridge from Santa Barbara. All right. So what is the thing I want to discuss? Well, I want to discuss the motivation for this project, or one motivation is just to study heat transport in strongly coupled field theories. And the fact that I'm here, and by my title, you'll see I'm going to specialize in what we now consider the easy case, those strongly coupled field theories that can be dealt with holographically. So what kind of heat transport problem am I interested in? Well, I should say that when I say heat transport, actually I'm interested in all transport phenomena. Heat transport is, of course, a very basic one. And I want to emphasize I'm interested here in studying it somewhat non-perturbatively, or at least in the regime where the heat transport actually generates entropy. Okay? So the comments I'll make here apply to any other transport phenomenon as long as they're occurring strongly enough that they also generate entropy. They'll have qualitatively similar characteristics. All right. I'm interested in heat transport, and we've had talks on heat transport in this workshop already. There was certainly one or two. Yes, please.
I'm really somewhat an outsider, but doesn't all heat transport generate entropy?
It does, except for some trivial cases. Of course, you can have just a fluid flowing with laminar flow at constant velocity. There's a simple case it doesn't generate entropy. And entropy generation is often second order in perturbations around equilibrium. So in linearized study, you don't see this. Okay? But yes, it's quite generic, and that's exactly my point. Thank you. Very good. So we've had talks about heat transport already, some by solving time-dependent numerical simulations, and some by looking at special cases. I want to emphasize that I'm interested in heat transport largely over finite distances in a field theory, for the simple reason that if you imagine that you have two heat sources, one at temperature T1 and the other at T2, if you move them infinitely far apart, then of course the average gradient of the temperature, delta T over L, goes to 0. And you tend not to see the heat transport in an interesting way. So I want to try to keep the heat sources at a finite distance. So I want to imagine that I have some kind of field theory, and I plug in some heat sources. Let's try to draw, just for illustrative purposes, one is hot and one is cold. I also like to think of my heat sources being finite sized. Okay? You could consider the infinite size limit, of course, but this is, of course, this is an interesting problem. I think of them as being finite sized and finite separation, one hotter and one colder. Now, if I want to couple a heat source to a field theory, I decide what kind of heat source it is. And I also have to think about what kind of coupling I want. Now, I actually don't know. I have no idea. I'm not a condensed matter physicist. I have no idea how the condensed matter community or the field theory community likes to think about these issues. But it seems to me complicated because in general there's a question of, well, what coupling constants do I want? Do I couple equally to all modes of my field theory? What does that mean? Okay, so from my perspective as a gravitational physicist, there is a simple, natural, and elegant solution to this problem, which is to choose to make my heat sources and sinks be simply black holes at temperatures T1 and temperature T2. Okay? Black holes coupled to any ambient theory by producing Hawking radiation and absorbing things. The coupling is universal in some sense. There's no coupling parameters to choose, although there are details of which black hole metric you wish to consider. Okay? So this is the problem I'm going to talk about. And again, I would motivate this as simply a natural way to couple a heat bath or a heat sink to a field theory. But you can also think about this as studying Hawking radiation in strongly coupled field theories. Okay, so that's my main motivation. I should mention that there is, however, going to be a choice of which black hole metric I use, and in principle, there can be dependence upon those details, although one hopes that the gross properties don't depend too much on exactly which black hole metric you choose. You might hope that the gross properties depend only on rough characteristics, like the black hole size, let's call it the radius r, and of course the temperature. Okay. I do want to mention that although as a relativist, I like this picture of black holes coupled to field theories, this is also, at least for the special case of a conformal field theory, which tends to be of most interest to this audience, this is very closely related to a more standard kind of heat bath that you might have thought of before. Might have. The point is, of course, that I'm going to consider the way you couple a field theory to a black hole is you simply study the field theory on some space-time that contains a black hole. That space-time has some metric. I'll call it ds squared. Okay? For simplicity, I'm going to consider static black holes. Okay? I won't define that term, but it's time-independent hypersurface orthogonal black holes. For static systems, there's a natural, for conformal field theories on static spacetimes, there's a natural conformal frame to study called the ultrastatic conformal frame. So think about defining a new metric, ds squared tilde, which is just some conformal factor times the old one, where the original metric was static, so I'll make a time-independent conformal transformation, and I can clearly use this conformal transformation to set the new tt component of the metric to -1. That's called the ultrastatic frame. So that's a conformal frame where there is now a trivial gravitational potential and only curvature of space. Okay? Yes?
The bulk metric.
No, this is the boundary metric.
The boundary.
This is the boundary metric. I'm so far only talking about CFTs. I will get to holography later.
So are you talking about a solution with two black holes, or?
So at the moment, I'm only talking about CFTs. So the metric is not dynamical. So I would not use the word solution. I'm talking about a metric with two black holes that I am free to write down by hand because it's just a background metric for my field theory.
So these black holes are the boundary metric.
At the moment, there is only a field theory. There is no holographic bulk. So yes, when we have ADS, when we do holography, the black holes will be in the boundary metric. At the moment, I am simply trying to couple heat sources to my field theory. And I'm trying to argue that putting the field theory on a black hole space-time is a very natural and elegant way to do that, which does not require me to choose details of couplings.
So your theory feels on the horizon.
The theory will feel the horizon. Yes, and this heat transport we're talking about can be thought of as simply studying the properties of Hawking radiation in that conformal field theory. It's equivalent, okay? Right. What we learned from Hawking years ago is that what black holes do is they heat things up. And that's really all they do.
metric now is non-dynamic.
This metric is non-dynamical, so I may choose it at will. It can be anything that I like. So I tailor it to suit my purposes. So please do not ask me about whether these black holes wish to attract each other. Okay?
But they cannot.
They cannot. They're pinned down and do not move. Okay? All right. And I can put them in these. Yes?
They also don't grow or shrink from their Hawking radiation.
That is correct. They do not. This is exactly why they act as heat baths. Since gravity is non-dynamical, they effectively have infinite entropy and do not grow or shrink in response to emitting or absorbing Hawking radiation.
But they will do if you put a cutoff.
I am not going to put a cutoff. You are correct. And putting a cutoff is an interesting problem. And what I'm going to say is closely related to studies of brain world black holes and other things. And I'm happy to discuss that with you. That would be a distraction from the main point of today's talk, but it's very closely related to that subject. And in fact, I think we've learned that you gain quite a bit of understanding about the case with dynamical gravity, the brain world black hole case, by considering this case where the black holes really lie on the boundary and there's no cutoff. Okay, this is a useful, slightly simpler context to understand certain things that can inform you the brain world context as well. Okay, good. So is that clear? That I am really talking about field theories on a non-dynamical black hole spacetime. Good. So my point is that if you change this ultrastatic conformal frame, the physics of any CFT will be unchanged. Okay, and what happens? Well, we don't even need to write down any equations. Black holes having black hole horizons mean that GTT in the original metric was 0 at the horizon. So to make it -1, we have to multiply by an omega that diverges at the two horizons. So you see that diverging conformal factor in the new metric will push the would-be horizons off to infinity and also make those spheres infinitely large. So in the new metric, the space-time looks something like this. Okay, where it has some spheres that grow at infinity, and it has some narrow bit in the middle here where you fix omega equals 1, and you don't need to make it grow. And then it has spheres that grow off infinity again. All right. And yes, please.
Does that mean that the backside of the black hole that's facing away from the other one isn't very different from the front side?
Backside of the, you mean, by backside, you mean what you get when you go sort of through the wormhole in the middle?
No, I'm saying the backside of this one on the right-hand side of the blue one.
It's not significant.
Thinking of these as droplets, it seems to me that the geometry is very different from the front side, which is closer. But you're saying because of this divergence, they're going to look like a plane boundary conditions at the end, right?
Yeah, it's not so different. I mean, I actually haven't drawn the full space-time here, but I remind you that conformal field theories are invariant under an inversion symmetry that maps infinity to the origin and so forth. So the backside is not obviously so different from the front side of conformal field theory. This is true. It can depend on details, but in general, the backside is not so different.
Another asymptotic region corresponding to asymptotic infinity in your original spacetime.
I was attempting to be ambiguous about that. I've only told you part of the space-time. Let's worry about those details later. This basic scenario admits many elaborations. You can choose the asymptotic region here to be various things. You could put the black holes. Actually, since Harvey asked, what I will actually spend most of my time doing is putting these two black holes on a sphere so that even the original metric is compact in the spatial directions, and there is no infinity. But you can add extra asymptotic regions as you like. In fact, what I'm trying to point out here is that certain kinds of asymptotic regions are conformally equivalent to adding extra black holes. I'll do a short calculation to tell you what the shape of these asymptotic regions is. So here, of course, I remind you that I'm in this ultrastatic frame. This is the tilde metric. And so this is simply the shape of space. There's no the gravitational potential is trivial across this space. So what's the shape of space? Well, we'll do a small calculation. We'll start with the metric. The asymptotic region here comes from the region here near the black hole. the region near any black hole, so no tilde, original metric, can be written as approximately Rindler space cross a sphere. So what's Rindler space? Well, there's some surface gravity kappa. There's a proper distance coordinate that I'll call xc, dt squared plus dc squared plus r, which is the size of my sphere. Think of this as technically a function of xc. As you get farther away from the horizon, r gets bigger. But in the near horizon region, near horizon, r is approximately constant. And then there's some sphere. Okay. So now we do our conformal transformation to the ultrastatic frame. It's very easy. You just divide by this factor. So in the ultrastatic frame, we find minus dt squared plus kappa to the minus 2 dc squared over c squared plus r squared over c squared d omega squared. And anyone who's done any holography will recognize this metric. It's Euclidean anti-de Sitter space, or otherwise known as the Euclidean hyperbolic space. All right. If I had chosen to start with planar black holes, I would obtain the same thing, but with the plane metric here instead of the sphere. I'd have Euclidean hyperbolic space in planar coordinates. So what we learn is that the black hole horizons are conformally equivalent to having extra asymptotically hyperbolic regions in your space-time. All right. Oh, with an interesting twist on this, you'll notice that the length scale for my hyperbolic space is kappa inverse. So the length scale set by the hyperbolic space is exactly kappa inverse. And those of you familiar with black holes will know that kappa inverse, kappa is the surface gravity of the black hole, which is effectively the black hole temperature. Okay. So this is proportional to 1 over the temperature of the black hole. So what you get after this conformal transformation is two space-times that are asymptotically hyperbolic. Their curvatures will be different if the black holes originally had different temperatures. And what you're doing by imposing a black hole boundary condition on the field theory is you're fixing the field theory over here to be filled with the fluid at temperature T1, and the temperature and the field theory over here to be filled with the temperature T2. With this interesting correlation that you've related the temperature to 1 over the length scale of the hyperbolic metric, and there's some number here that I haven't written down, some coefficient of order 1. All right. Good. Now, I will mention that this conformal frame suggests an interesting generalization of my original problem. Of course, from the field theory point of view, there's no reason that you have to have this constraint. It would be fine to consider a large blob of fluid here, an infinite bit of fluid that effectively acts as a heat bath, okay, without requiring a correlation between the temperature of the fluid and the curvature of the metric it's on, right? We do this all the time. So I could choose then to break this correlation and conformally transform back and ask what I get, okay? Well, obviously, I haven't changed the metric. All I've done is change the field theory boundary conditions. So this problem is, so I call this, or we call this, the detuned case, in contrast to the tuned case that comes up naturally here. In the detuned case, you're still talking about a conformal field theory on a black hole background, but where the conformal field theory is now not in equilibrium with the black holes, okay? What that means is that the quantum state of the conformal field theory will no longer extend smoothly across the black hole horizons, okay? But you can still talk about that. In relativistic language, the region outside the black hole boundary, the black hole horizons, is a globally hyperbolic space-time. I could restrict to just the exterior and work there and choose to consider the field theory at a temperature which is not the black hole's temperature. This is perhaps best explained from the Euclidean point of view. You know that you can describe the tuned case, where the state of the field theory is smooth across the horizon, can be defined by writing down the CFT state as a path integral on the Euclidean black hole spacetime, where you identify the period of Euclidean time to make the Euclidean horizon smooth. Okay? You could choose to do something different. You could choose to use a Euclidean black hole spacetime where you allow a conical singularity at the horizon. Okay? With appropriate understanding of the conical singularity, that also gives a well-defined path integral. It just does this detuning. Okay. So I want to mention that. That's a slightly less natural thing to do from my original perspective of working with black holes, but it's not a ridiculous thing to do, and it will turn out to be technically useful to allow that detuning at certain places in my talk. So this is a slight aside. In general, you should assume I'm working with the tuned case, where the quantum state of the field theory is smooth across the black hole horizon, and we could be discussing the full black hole geometry, including the interior, if we wished, although that's not so relevant to my heat transport problem. But at one or two points, I will consider the detuned case for technical control and for illustrative purposes. All right? Okay. Great. Yeah. Oh, and let me mention what one of those purposes is, actually. Of course, the easiest way to study heat transport is to use the hydrodynamic approximation. All right? So you should ask, when is the hydro approximation good for my problem? Well, at some rough level, the hydro approximation should be good when the gradients are small. So when the temperature difference divided by the temperature is much less than 1. Temperature difference divided is I need to get the length scale L in there. I'm not going to get this exactly right now, but anyway, when the gradient dt dx is sufficiently small, the hydro approximation should be good. All right. So you might think that you could make it good by taking the two temperatures close together. Well, it turns out that the hydro approximation always fails near the black hole horizon in the tuned case, as you can see from this picture. In the tuned case, if I require the temperature to be related to the length scale of the curvature of this hyperbolic space, well, that means that you're not in the high temperature regime, right? The thermal wavelength of the CFT is comparable to the curvature of the space, and it knows about it. So you're at least not parametrically well into the hydro regime. All right. So there's some breakdown of the hydro approximation in the tuned case, but by passing to the detuned case and allowing myself to take the field theory temperature much higher than the black hole temperature, I can reach a correspondence with the hydro regime, which is useful just to get some insight into what happens, and also technically useful when you're doing numerics to give you a place to check your codes. And of course, it's also conceptually interesting, because when I finally show you a plot, assuming I get that far in the talk, there's some interesting behavior that arises when you leave the hydro regime, and it would be wonderful to have a theoretical explanation of why that behavior occurs.
I'm a little bit confused.
Yes.
Precisely in the cases where we derive hydrodynamics from gravity,
Yes.
you have to go very close to the horizon and only
The
consider
bulk horizon. The
low-
bulk horizon. Very close to the bulk horizon.
Right.
And consider long wavelength,
Right.
and you want the boundary conditions and the boundary vevs to vary very slowly compared to the temperature.
Right. But
Here I have no bulk yet. This is all on the boundary. And the point is that the curvature scale here is relatively close to the thermal wavelength in the CFT. So the background fields, the sources for the CFT are varying on a scale comparable to the thermal wavelength. And the same thing happens here. Said differently, maybe it's even more obvious in this frame. So the wavelength of Hawking radiation is always at a given. So in this frame, the local temperature of the Hawking radiation varies. But when you're close to the horizon, the thermal wavelength of Hawking radiation is always comparable to the distance to the horizon. Okay. So there's a feature there which takes you out of the hydro approximation. By some order 1 amount. It's not that the hydro approximation is failing by parametrically large amounts, it's just failing by an order 1 amount. Okay. That's interesting.
If you
Yes,
fix
please.
the tuning, you're still far out of equilibrium because the fluid is not in equilibrium with the Hawking radiation.
Okay. the tuning here, let's think of it in this frame, which may be simpler. In this frame, there's no black hole. So you see that equilibrium has to do with whether the fluid temperature on this side is equal to the fluid temperature on this side. Detuning itself has no effect on whether you're in or out of equilibrium. And the same is really true here, because what the detuning does, let me draw for you, oops, oh, that's interesting. Let me draw for you a conformal diagram. So think of, here is the hot black hole horizon. Here is the cold black hole horizon. This is an impressionistic conformal diagram. In the detuned case, you're still imposing a boundary condition on the temperature of the fluid right along the horizon. Okay? And because it's a boundary condition, it can't change dynamically. There's nothing here that would allow the fluid near the horizon to, quote, come into equilibrium with the black hole it's next to. Their temperatures are fixed to be different by a boundary condition. And you might think of it this way. The black hole, the actual influence of the black hole is, of course, causally shielded from the outside. So the fluid just outside, if I've told it what temperature to be at, can't be sensitive to what the black hole is doing. So it's just a funny thing in the field theory. All it really means is that the fluid stress tensor will, in the detuned case, the fluid stress tensor will diverge on the horizon, whereas in the tuned case, the fluid stress tensor is smooth across the horizon. Okay. All right, any further questions? All right, so now we get to Elias's question. What is the holographic description of this system? Well, to use holography, we take our CFT and we make that the boundary of some anti-de Sitter spacetime. So the spacetime on which the CFT lives, this black hole spacetime, will now become a boundary metric, and we want to find asymptotically ADS solutions which have that boundary metric. So if I think about this as the boundary of my ADS space, it will contain two black holes. I'll draw one of them for the moment. Okay? And if there's a horizon in the boundary metric, then it seems intuitively clear, and in fact it's true, that the bulk must also contain a horizon that must connect to the boundary. So we could try to find such solutions and study them. Now, there was an interesting historical puzzle in this line of work. As far as I know, the first people to try to use black holes coupled to a CFT holographically were Myers and Estefani in the late 1990s, and they never published their work, although Rob gave some talks about it, because their results were confusing. Okay? They found that when they made a bulk solution that had this horizon on the boundary, they found no Hawking radiation in the CFT. They found that coupling a black hole to their CFT did not result in any radiation at all. And that was confusing. Okay? Let me draw for you a picture of the solution they used. Their bulk horizon looked like this, something that we now call a black droplet, because it kind of hangs down from the ADS boundary. Okay? And you can see the issue here in retrospect. If you wanted to find Hawking radiation, so in this case, think of one black hole and imagine that we just have an asymptotically flat black hole spacetime. Suppose you wanted to see a heat flux going this way. All right. Well, in the bulk, the horizon just stays right here. So the only way that the bulk can transport heat to field theory infinity is through bulk Hawking radiation. Okay? Bulk Hawking radiation is an order n to the 0 process. Okay? And you don't see it at the classical level. All right? What you need to see Hawking radiation to infinity at the classical bulk level is you need a horizon that extends to infinity. All right? And that's where Mukund and Veronica and I entered the game. And we basically argued that in addition to these droplet solutions, there should be other families of solutions, although it's interesting to think about their properties. So this droplet solution, it exists. You can find simple analytic toy models in weird cases, or you can work very hard, as Toby Wiseman and Pau Figueres did, to find the exact solution numerically in a more natural case of, say, Schwarzschild black hole in the boundary. followed up by some of my other friends over there. But if you have this solution really just has this droplet horizon, and of course, this is ADS. Implicitly, there's a Poincare horizon down here infinitely far in the bulk. It seems pretty clear intuitively that you can imagine raising this Poincare horizon, which is equivalent to filling the CFT with plasma at a non-zero temperature. As long as the temperature of this plasma is fairly small, I'll draw it in blue because it's fairly cold, it's going to be far away from this droplet and not have much influence on it. So an interesting point is that you can be in a phase of theory where you're clearly deconfined, where there is some plasma in the CFT, and it simply doesn't couple to this black hole. There's at leading order in n. It couples only at order n to the 0. On the other hand, as you keep increasing the temperature of this plasma, holding the black hole metric constant, it's clear that you'll eventually reach a point where something more interesting happens. Okay? And so we suggested that there should be another phase of this system with the same boundary metric, which, for lack of a better term, we called, oops, that's this one, we called a black funnel. And if you could find such solutions, it's pretty clear that if you could manage to set the temperature here to be different from the temperature over here, that it would conduct heat in a way that you could see at the classical level in the bulk, at leading order in n squared. All right. Very good. So let me move on. Let me now try to be a little more precise about what context I will explore in detail in this talk. As I mentioned to Harvey, a context which turns out to be, technically useful is to think about having my original two black holes in the field theory on an otherwise compact space. So said better, think about starting with the CFT on a sphere. Here we go. There's a sphere. And I will then add to my sphere one hot black hole and one cold black hole. All right?
Are analytic solutions known for a Schwarzschild black hole on a sphere?
For a Schwarzschild black hole, you mean solutions to Einstein gravity? Yes and no. Hold on one moment. Okay. Yes and no. First of all, I remind you that this need not be a solution because it's a background metric I get to choose by hand. Okay, so I can choose it by hand. The right answer to your question is that if I'm working with a CFT, all I care about is the conformal structure. And there are metrics of this kind which are conformally equivalent to a pair of Schwarzschild ADS black holes. And so that's one reason why I like this picture, is there is a nice Einstein metric I can choose, okay, which has the same conformally invariant physics as this setup. All right, great. So I want to study this problem, and in analogy to what I just said, there are two obvious phases to consider. There's this sort of droplet phase, where each black hole horizon dips down into the bulk just a finite amount, and there's also going to be some kind of funnel phase where there's some flow somehow that gets cooler as it goes across, like this. At least these are two natural phases to study. All right. I guess this one is perhaps not very exciting. It seems intuitively clear that if I could imagine having once I have a funnel solution like the one that Powell and Toby Wiseman found for us, I could put two of those together. And there's clearly no obstruction at the level of classical GR to making these different temperatures. It's just a matter of constructing the solution in detail. In fact, it's clear enough that I don't think anyone has bothered to construct this double droplet solution with two detuned temperatures yet. It has not been considered an interesting problem, although it technically might require some work. This one is more interesting for several reasons. One is this is the one where you're actually going to get heat flow. And therefore, you should see entropy generation. Okay? That makes this a sort of novel kind of horizon from the standpoint of general relativity. Okay? Because I've set up my boundary space-time to be static and time-independent. So physically, we expect a time-independent solution in the bulk. So we expect that this should be stationary. Okay. On the other hand, we also expect that in some sense, there is a position-dependent temperature in the bulk horizon. Okay? And that intuition is in contrast with normal GR intuition for more normal kinds of black hole solutions, where we have something called the rigidity theorems. The rigidity theorems tell us that if you have any stationary black hole with a so-called compactly generated horizon, that it in fact has additional killing fields so that it has a killing horizon, and its event horizon is in fact a horizon for some killing field. There's some symmetry associated with it, such that, well, first of all, that means there's a well-defined, unique, constant temperature. This is often called the third law of black hole mechanics. All right? And it also means that if you follow any one horizon generator, that it's sort of the same at every place along the generator. Whereas here we clearly expect the generators to sort of flow from the hot black hole to the cold black hole as the fluid would in the fluid gravity analogy. So the point here is simply that these theorems that I mentioned, these so-called rigidity theorems, hold for what are called compactly generated horizons. That means if you take the horizon and take a slice of it, which you might think of as a constant time, say Eddington-Finkelstein time, that surface is compact. Well, it's clearly not true here. These horizons extend to infinity from the point of view of the bulk ADS metric. So not compact. Right? And physically, these theorems are easy to understand from a thermodynamic point of view. If you imagined you had some compact blob of stuff, and in this sense, compact also means self-contained, so you're not driving it, and you let it sit there, it's going to come to equilibrium, and there'll be no flow across it. Here, it's clear that we have put boundary conditions on our ADS system that drive some heat flow. So that's why it's different. Okay. But it's novel and interesting. So it's stationary, and because of this gradient so gradient of temperature is a temperature gradient, it means it's a non-killing horizon. Okay. It also means a couple of other things. So one of them is that, as I say, we expect heat transport. But anyone who studied Hawking radiation knows that just as in, say, the Unruh state for the Hawking effect, whenever you have a flux of stress energy coming out of a black hole, of a stationary black hole, and if that flux is time independent, it follows, because of the blue shift at the horizon, that there must be a divergence of the field theory stress tensor on the past horizon of the black hole. So this suggests a singular past horizon in the bulk. Okay. So we're used to thinking about stationary black hole solutions as having a past and future horizon. In this case, it's natural to expect that the sort of bulk conformal diagram has a nice future horizon, but a singular past horizon, and therefore also no nice bifurcation surface. Something to be aware of. Okay. Good. That means, in particular, that if you're interested in finding these stationary solutions numerically, you can't use the techniques that were developed by Toby Wiseman years ago for finding other kinds of stationary black holes. Said differently, the Euclidean continuation of these black holes is not going to be very nice. All right. Nevertheless, you can find new techniques and solve the problem if you work hard enough. Okay. Oh, a last comment related to this. The fact that we also expect entropy to be generated in this heat flow. As a result, we expect that the generators of the horizon, the null rays along the horizon, have positive expansion. Okay. In GR, we measure the area of the changes in the area of the horizon by looking how much the area changes along a given null ray along the horizon. And it tends to expand as time passes. There's a theorem, though, which says that if the expansion is non-zero at any finite point, then if you follow it back into the past, it actually must have been, let's see, did I get this right? Oh, well, anyway. Sorry, it's non-zero, but it must vanish asymptotically far in the future because it's a stationary horizon. So it goes to 0 as, I'll call it, well, as some parameter goes to infinity. There's a theorem that says that if this is true, the expansion must have been negative infinity at some finite place in the past. All right. Did I have my signs right? I know I don't. Anyway, there's a theorem which says that there must have been a caustic in the past at a finite affine parameter. So this again suggests a singular past horizon, and it suggests that these generators of the future horizon are emerging from this singularity at finite affine parameter and then proceeding on to the future. This is the picture we expect. Okay, very good. I guess the next thing I wanted to do is to show you some results of some numerical simulations. So Sebastian Fischetti, George Santos, and I attempted to construct solutions like this numerically, and there's some very similar work, although in a different context, by Toby Wiseman and Paulo Figueras. So I wanted to take a moment to show you what we did. At some level, there's not much to show. The answer is we found a solution, and it has heat transport, but I'll show you some plots to make you happy. All right, now, the question is how to actually get my computer, how do I display this? Whoever's in the back room can help me turn this on. Oops, what am I supposed to do? There it is, thank you. I thought a verbal cue might do the trick. All right, unfortunately we have to wait for my very slow computer to wake back up. But I'll mention that the main point of doing this is just to show you that numerical techniques do now exist that can solve for these stationary flows in the bulk. You could, of course, also solve this using a fancy time-dependent code if you had a strong enough one. You could just set up arbitrary initial data and see what it settles down to. But for us, it seemed more natural to try to solve directly for the stationary solutions. And so I'll show you what they look like. And I'll also show you, good, what the physics is here. All right. So what we did is to consider a setup that looks like this. We fixed the boundary geometries. So we fixed the black hole background that the CFT lives on. And we decided to introduce this detuning parameter I mentioned for some technical control. So these are plots of fluids flowing over the same geometry. If you like, they're flowing over this same, I wonder if I can push this far enough down you can see it, same hyperbolic geometry. And we started with the tuned case that really represents a smooth black hole state. And we also then increased the temperature of the fluid relative to the temperature of the black holes. Now, boundary is what?
S3?
S3 except for the black holes. Yes, in fact, we are working in four bulk dimensions, yes. So in fact, in this case, I'll tell you what we did. We chose the boundary to be conformally equivalent to a pair of BTZ black holes. You will remember that 2 copies of ADS3 can be glued together so that they are conformally equivalent to S2 cross R. Oh, sorry, S3. Which dimension am I in? Sorry. Wait. These results are for 2 + 1 boundary dimensions. Sorry, 2 + 1 boundary dimensions. So our space-time, the CFT should be thought of as living on a space-time that is S2 cross time, with the S2 punctured by 2 black holes. And in fact, it's precisely 2 copies of BTZ conformally sewn together at the boundary. Okay, but analogous results should work in higher dimensions as well. All right. So the way to read this graph is to first find 0. Okay. And then, fairly obviously, the stress tensor is larger after we heat the system up. So the curves that are farther from the origin are more detuned. The blue curve is exactly tuned. The red curve is, here, let's see, my captions down here. The relevant numbers are,
So rho is the bulk coordinate.
these are all plots of the boundary stress tensor. These are all boundary coordinates. So there's the time coordinate of the boundary. Phi is the azimuthal angle on the boundary. And rho is some coordinate that runs between the two black holes. Okay. So the black holes live at the edges, plus and minus 1. If we think hard, we can figure out which one is the hot black hole and which one's the cold black hole. What I want you to notice is, so of course, the dots are numerical data. The lines, dashed or solid, are the fluid approximation. Okay? In the detuned case, for these yellow and red curves, the fluid approximation is excellent. And here the detuning is only by about 30%. Okay? So the completely tuned case has a parameter we called alpha equal to 1. The detuned case is alpha equals, this is alpha equals 0.7, and this is actually 0.8 or 0.77, actually. So as is often the case, the fluid approximation does very well, even when you are fairly far from what you might have thought as the naive regime of validity, even when you're having thermal wavelengths comparable to gradients by an order 1 factor.
Sorry, I'm a little bit confused. This is the boundary data, which means you choose them, right?
This is the stress tensor, so we compute it. It's not the boundary metric, it's the
not the
boundary stress
metric,
tensor.
it's the stress tensor after solving the bulk Einstein equation.
Correct. Correct. So we chose a boundary metric, and we compute the boundary stress tensor, the usual game. All right. So it's interesting, of course, that as we've seen in so many other talks in this program, the fluid approximation works very well over a large region. Okay. It's interesting, however, that that in this short transition from 0.8 to 1, we do see a qualitatively different behavior emerges that separates the numerical data from the fluid approximation. And in particular, it's interesting, the fluid approximation doesn't seem to really know the difference between the hot and cold black hole, except for the overall sign of that one, the heat transport term. If you swap the black holes, the heat flows the other way, and that sign changes. Everything becomes positive instead of negative in our conventions. Okay? But the actual CFT coupled to the black hole does seem to know the difference. There's an anti-symmetry of the endpoints. I should say that we don't have a really sharp theoretical understanding of why this occurs, but it's certainly an interesting phenomenon, and especially since it seems to appear so rapidly. That, of course, could be an illusion. It could be that the same thing is happening here and here, that the fluid approximation is still breaking down very close to the edge, but maybe you just have to go farther and farther out. That seems unlikely, though, because in the extreme limit of the detuned case, it's just a hot fluid on a hyperbolic space-time, and why should anything funny happen near the boundary? Yes, Veronica.
You have sort of a tension at the hot end, or which end is the hot one?
I can't remember.
One of them you have sort of effective tension rather than pressure of the fluid.
That is correct.
As you
That is correct. And said differently, if you go up the top, you'll notice that this is an obvious breakdown of the fluid approximation, or a feature the fluid approximation can't capture. You have a negative energy density near one end and a positive energy density near the other. Now, actually, I said we don't have a sharp theoretical understanding, but it's true in many cases where you can study free field theory stress tensors near horizons, or you can have good approximations for it. It is often true that Hawking radiation is characterized by having a negative stress energy near the horizon. Okay? So, as I say, so there's some rough understanding that in the true fluid regime, the stress energy should be, the energy density should be positive everywhere, even at the horizon, because the horizon is conformally equivalent to infinity in hyperbolic space, which is pretty regular. And based on simple examples, there is perhaps some intuition that the stress energy should be negative near the horizon in the tuned case. But those were just simple examples. Most of them are weakly coupled. We don't really know what that means. And here we find that it's only true that the energy density goes negative at one of the horizons. So there's lots of room for asking interesting questions and some people in the audience generating interesting answers that I don't have today. Mukund.
I mean, this negative energy density you could argue by asking for the stress tensor to be regular on the horizon. So one argument goes that some TT plus rho component or whatever in the local Rindler frame has to have a definite behavior. How does it work in the other end?
Because the rho component changes sign too.
So you say because the pressure becomes tension.
Yeah, that argument couples what's in these coordinates is a divergence in the tension with a divergence in the energy density. The signs have to be correlated. Okay, it doesn't tell you the absolute sign.
So basically, you just say that in the ingoing coordinates, whatever the ingoing.
You must have smoothness. That's right. That's right. So there is much here to explore further. Very good. All right. So this is the what you get in the time-dependent case, and it's interesting that there is some novel feature when you leave the fluid approximation, and we'd like to understand that better. I will mention that we also confirmed numerically this picture of the past horizon as being a singular surface from which everything emerges. So it's a nice, consistent solution for this non-killing horizon with heat flow. All right. I have just a few more minutes, and I wanted to say something about some new work. Let's, I can leave that. Yeah, I'll work over here. I'll leave that up for a moment. Well, new work, old work, there's so many things to discuss. I wanted to talk about the structure of phase transitions here. So there are two solutions. It's natural to ask, which one does the field theory like best? Okay? Could we compare the free energies of these solutions? And let me not for the moment worry about what I mean by that in the non-equilibrium context, but let's go back to equilibrium for a moment to make life easy and let the temperatures of the two boundary black holes be the same, okay? And talk about whether this phase or this phase should be dominant. Let me first mention that in the case of a 2+1 CFT, or ADS4, Mukund and Veronica and I had a lovely analytic treatment of this question, which I have to say, it's my favorite part of a certain paper we wrote, and it's kind of buried in one little section that you have to look for it to extract, so I'll mention it here. We argued that at least the interesting phases in this context can be found completely analytically, and the phase transition can be studied analytically as well, by a lovely trick. The trick is the following. As what we want to do, I'm sorry, not with special choices of the boundary black hole metric, the phases can be found analytically. So we consider the 2+1 CFT, again, on this space-time where the CFT space-time is a BTZ black hole glued to another BTZ black hole. This is just the same boundary metric we use for our numerical simulations here. Let's see, I had a simple way of saying this.
These are the same temperature?
At the same temperature. T. So equilibrium.
And this final solution exists for the same temperature?
Let me explain. Okay. Let me actually start with a very familiar bulk solution. Let's start with ADS4. ADS4 we can draw as a cylinder, and its boundary is S2 cross R. There's ADS4. Very good. So the boundary is, I'm trying to do this, ADS4. Right, so the boundary is a space-time you might call ESU3, the three-dimensional Einstein static universe, which is S2 cross R, which if I draw a picture of it, it looks kind of the same. But in this case, we have a solid cylinder, and in this case, it's just the cylinder. All right. Now, as is well known, you can cut this in half along the equator of the S2, and this is conformal to two copies of ADS3. So I'll write it as ADS3, I don't know, times 2. I'm not sure what the right mathematical notation is for gluing two things together this way. But each half of this is conformal to ADS3. On the other hand, those of you who are string theorists or quantum gravity people will recall that Euclidean ADS3 with a finite period and a finite temperature is the same geometry. It's isometric to the BTZ black hole. Or in other words, that a double Wick rotation of ADS3 gives the BTZ geometry. If you analytically continue in both time and the azimuthal angle, you convert ADS3 to BTZ. So you see that my problem with two copies of BTZ on the boundary is related by double Wick rotation to the problem with two copies of ADS3 on the boundary, which is related conformally to the standard boundary conditions for ADS4. All right? So if you have any solution of ADS4 which admits a U1 cross U1 isometry, which is, let's say, static and has a time translation, and it has a rotational symmetry, you can Wick rotate it twice to get a solution we want. And we think we understand phase transitions in ADS4 with standard boundary conditions. That's Hawking-Page. So let's just draw a few last pictures here. What are the phases for Hawking-Page? Well, there's empty ADS, which you might think of as thermal ADS. So this is just empty ADS. There's a large black hole, like so, and then there's a small black hole. All right. Now, I want to do a double Wick rotation. So I want to Wick rotate in time and also in the azimuthal angle phi. So let me also draw on here the axes of rotation for the azimuthal angle. So it's just the axis that goes from the North Pole to the South Pole. It looks like this. Here it runs into the black hole, and here it runs into the black hole. Now, anyone who's done this before knows that double Wick rotations exchange horizons with axes of rotations, because in the Euclidean solution, for a static geometry, a horizon is just an axis of rotation. So after the double Wick rotation, after the double Wick rotation, and let me actually make this picture easier to read by erasing half of it. You see, if I'm going to think about this as a slice at constant t and azimuthal angle phi, I don't need the second copy. Wait, I don't want to do this. Right, because if this is azimuthal angle 0, this is pi. It's a different phi. So let me just draw slices at constant t phi to make this easier to read. So there's that bit, and here's this bit, like so. And now, if I imagine, so my dashed lines were axes of rotation, and the solid lines were horizons, but if I just change the interpretation, then you see this is now a horizon that runs from one end to the other. In other words, it's a funnel phase. And this is a horizon that goes a certain distance into the bulk, where it reaches the axis of rotation, and there's another horizon here. And that's exactly a droplet phase, because here's the axis of rotation, and it looks like that. Okay? So you see, in ADS4, for the BTZ boundaries, we can find all of these solutions analytically. And then we can compute the phase transition analytically. And it's Hawking-Page. So, what it looks like is this. Here's our phase diagram.
The temperature in Hawking-Page maps to what here?
So the thermal circle of Hawking-Page maps to the rotational circle around this phi axis, and vice versa. So roughly speaking, high temperatures for Hawking-Page map to low temperatures here. T goes to 1 over T. It's an SL2Z transformation on the torus. So it's the the S transformation. Okay, it means S duality in some language. Anyway, so the phase looks like this. Okay, the free energy of any of these solutions is in some sense is in some sense infinite, although you could make it finite by counter-term subtraction. But the meaningful thing to do is to plot the finite differences in free energy. So let me plot F delta F, which I take to be F minus the funnel solution. So the funnel then lies along this axis by definition. And of course, it's Hawking page. So what you find is a finite temperature at which the droplets nucleate. When they nucleate, they're not preferred, but at some point they become preferred. So there's I'll call this the short droplet and the long droplet phase.
What is the horizontal axis here?
It's the radius of the BTZ black hole divided by the three-dimensional boundary anti-de Sitter length scale.
What this has to do with the temperature of the boundary black holes?
Well, good. BTZ black holes have a certain temperature characterized by their radius, and for BTZ black holes, this is proportional to the temperature in units of the boundary anti-de Sitter radius. So temperature increases this way. All right. So I'm over time here. I suppose I should really cut this off, but I wanted to say, yes?
Just reading it. So the funnel phase is true at high temperature?
The funnel phase, so we want to
it splits apart in the droplets.
That's right. There's the droplets appear here, and there's a first order phase transition here. Okay. I wanted to say a few words about current work, which is very soon to appear with George Santos, which is a similar discussion in 5 dimensions, where the solutions cannot be found numerically in general. Although it turns out that analogs of these funnel solutions exist in arbitrarily high dimensions and can be found exactly analytically as long as you put Schwarzschild anti-de Sitter black holes on the boundary, as we learned from a paper by Simon Ross and Ruth Gregory and Robin Seggers, but I guess was known before that by various people. And so I just thought I'd mention very briefly that in the 5-dimensional context, in any case when the bulk dimension is 5 or higher, there's a physically new phenomenon that comes into the game. It's the bulk Gregory-Laflamme instability. Okay? In 4 dimensions, there's no known notion of Gregory-Laflamme instability. Okay? Now it's interesting that it is sort of true that if you take these BTZ black holes to be small, that this bulk funnel solution now does look a lot like a 4-dimensional black string that you might have thought shouldn't exist. Well, it's the same story as you might have thought before BTZ that 3-dimensional black holes shouldn't exist, but they sort of do. All right. Anyway, it turns out that it is true that this black string, the BTZ, the funnel in ADS4 that has BTZs on the end, is perturbatively stable for all values of the BTZ black hole radius. There's no Gregory-Laflamme instability. In 5 dimensions or higher, though, there's a corresponding analytic solution that has Schwarzschild ADS on the boundaries, and it does have a Gregory-Laflamme instability when you make the boundary black holes sufficiently small. Okay. That gives a new feature to the phase diagram. All right. And let's see. I guess I'll tell my computer to wake up while I'm giving you the intro to it, because my computer has again gone to sleep from my not touching it. All right. But basically, what happens now, the interesting part of this is that, from our perspective, is the Gregory-Laflamme instability not only makes certain phases unstable, but gives rise to new phases as well. All right? Because those of you who know this story will know that in the usual zero cosmological constant case, you can look at the point where you make the string thin enough that you get a Gregory-Laflamme zero mode. Then you can follow that zero mode as it gives you non-uniform black strings with bumps on it. And at least in low dimensions, in the zero cosmological constant case, those non-uniform black strings exist as static solutions, but they're actually even more unstable than the original solution. Okay. Here, similarly, you can find a boundary condition where the zero mode turns on, and you can follow it. And in this case, the Gregory-Laflamme zero mode, well, the zero mode goes like this, so it makes parts of the string thinner and parts thicker. if you had a translationally invariant string to start with, it doesn't matter which part gets thick and which part gets thin. Making this part thin is just translationally, is related by a translation to making this part thick. But here, the ADS gravitational potential gives you preferred middle. And so thin strings and thick strings are different. All right? And what's interesting here is that if you follow the zero mode far enough, in the direction where you thicken the funnel, it merges with it becomes another solution that you might have expected, which looks like this. We call it the fat funnel. And it is essentially a large spherical bulk Schwarzschild black hole with a little bit tacked onto the end to make it a funnel. And I'll be done in 30 seconds. If I say those words, you'll believe that that phase should be stable because, of course, large and dominate the thermodynamics because, of course, large bulk black holes minimize the free energy in the bulk under simple boundary conditions. So we see some of that, and I will show you one plot, and then I will stop so that we have plenty of time to enjoy Harvey's talk. All right, so here's our current data. All right, maybe we can dim the lights just for a second so we can look at this. In this case, we have plotted the free energy delta F. This is, again, the free energy compared to the analytic funnel solution, what we call the uniform funnel. We've plotted it against temperature here, which is not really the best way to show the data, but will work for now. And what's interesting is that these blue dots here, these are all the fat funnels. And all the interesting phase transition structure is up there near 0. In other words, one of the interesting things that happens in 5 dimensions is that all these phases I talked about exist, but a lot of the structure comes in at incredibly tiny differences in the free energy in units where the ADS scale is 1. It's an interesting feature. We expect it to become more clear in higher dimensions. In other words, in this dimension, it turns out, so when that zero mode, that red dot is where the Gregory-Flamm zero mode turns on. The purple or red thing going up is the thinner funnels. Initially, the thicker funnels also go up in free energy, but very quickly they come back down. So you have a first-order transition between the uniform funnels and the fat funnels, but it's very weakly first order, very weakly. All right. And eventually, if you follow those thin funnels up far enough, that's them coming in here, the purple ones, they merge with the blue curve, which is a droplet phase. So that did not happen in 4 dimensions, but in 5 dimensions, when the funnel gets thin enough, it really does pinch off smoothly in what we believe is a cone transition, for those who know what that means, into 2 droplets that separate and go away. So that's our, this is still a little bit in progress, but that's our data so far. Thank you very much for your indulgence, and I apologize for running over time.
There are only very urgent questions. We are already over time. We can discuss in private anytime.
Very good. Thank you.
Thank you again.